So my name is Jordan Swaim Fox. I'm the Outreach Coordinator for the Center for Urban and Regional Analysis, or CURA, at Ohio State. And we're glad to have you here today for our third webinar in the series, Is AI Sustainable? We're co-sponsoring this series with Sustainability Institute and the Translational Data Analytics Institute. And throughout this series of talks, we're hearing from experts on the ramifications of the expanding use of AI and growth of data centers. Today, David Rolnick will discuss how AI is being used to help tackle climate change and other implications. But before we introduce David, I just want to mention a few logistical items. If you require closed captioning today, you'll find a box at the bottom of the screen labeled CC. Click this box and select Show Subtitles, and this will allow you to view subtitles during the presentation. At any point during the webinar, you can submit questions using the Q&A box. We'll ask as many of your questions as we can in the last portion of the presentation, and if we don't get to your question, apologies in advance. You'll notice that the chat's been disabled, so use the Q&A box if you have any information to share with the event organizers as well. You may have seen that this event is approved for 1 AICP CM credit, and to claim your CM credits, you can log onto your My APA account on the APA website and enter the event into your online CM event log. There'll be a brief survey that pops up at the end of the webinar, and if you have time, we'd love for you to provide your feedback to help us improve these events. Any additional questions after the event, you can email me at swaim-fox.1@osu.edu. Finally, to learn more about our future events at CURA or to sign up for our monthly newsletter, you can visit cura.osu.edu. You can also like CURA on Facebook and follow us on X and Instagram. You can learn more about Sustainability Institute and TDAI at si.osu.edu and tdai.osu.edu, respectively. With that, I'll pass it over to CURA's director, Harvey Miller, to introduce our speaker for today.
Okay, thank you very much, Jordan, and welcome to the third in our spring 2025 webinar series on Is AI Sustainable, where we're looking at the environmental, climate, social, economic, and energy impacts of AI and data centers. And I'm pleased to introduce our speaker today, David Rolnick. He is an assistant professor and Canadian CFAR AI chair in the School of Computer Science at McGill University and at the Mila, Quebec AI Institute. He is a co-founder and chair of Climate Change AI and serves as the scientific co-director of Sustainability in the Digital Age and co-lead of the Global Climate Center on AI and Biodiversity Change. Dr. Rolnick received his PhD in Applied Mathematics from MIT. He is an AI 2050 Fellow and a former NSF Mathematical Sciences Postdoctoral Research Fellow, NSF Graduate Research Fellow, and Fulbright Scholar. And he was named to the MIT Technical Review's 2021 list of 35 innovators under 35. So he has a great portfolio, great record to bring to us today. And now I'd like to turn it over to you, David. The floor is yours.
Thank you so much for having me. It's a pleasure to be here with you. I should note my internet just got a little bit unstable, so let me know if there's any issue, and I'm happy to repeat something. Let me share my slides here. Okay. So I'm going to be talking about AI and climate change. And I know that you've all been listening to a lot of different talks that combine these two topics. And I want to start out with the way that AI and climate change as a topic is often framed, and then tell you why I think that we should all be maybe thinking about it a little bit differently. So this is the way that AI and climate change is often framed. How AI can tackle climate change. AI is going to solve challenges across many different areas of climate action. List of applications keeps growing. There are ways from detecting methane to preventing fires that AI is going to solve a lot of our climate problems. On the other side, training a single AI model can emit as much carbon as 5 cars in their lifetimes. OpenAI CEO says that their AI systems are going to require there to be tremendous breakthroughs in how much energy can be produced by the world because we just need that amount of energy. And that AI and climate change are colliding. All of these things are true insofar as they go. But the framing that they lead to is often AI can help solve climate change, but it uses a lot of energy. And I want to talk about why I think this framing is very problematic. But before we can get into why it's problematic, I want to talk about each of those pieces because both sides of this two-sided perspective are in some sense right. There are a lot of ways that AI can help tackle climate change. This is the primary focus of my own work. We've analyzed a lot of different sectors and specific applications for AI to help advance climate action. And that's not just like AI in the future, that's AI right now in areas from climate modeling and prediction to the built environment to heavy industry, agriculture, forestry, and other land use, electricity systems. Many other sectors are already being transformed by AI in ways that are aligned with climate action. Also not aligned with climate action, but we'll get to that later. I want to talk about some overall themes for where we're seeing AI making a difference in climate action. If you're interested in more details, by the way, you can check out this full paper. It's about 100 pages worth of applications. And there's also a version online that you can actually search by particular sector or kind of AI. But the overall themes that I want to touch on are, first of all, improving operational efficiency. We're seeing AI being incorporated into systems like HVAC in buildings, residential, commercial, industrial, to use less energy. From smart thermostats to complicated operational control systems that are just reducing the amount of energy needed to heat and cool a building. Steel and cement manufacture, together contributing about 15% of global greenhouse gas emissions, are being optimized by AI algorithms. And even small optimizations to use less energy or use less raw material, which also contributes to less energy and greenhouse gas emissions, are great for the industry and can have great impacts on climate change, just given how large those sectors are in terms of their sheer quantity of impact. The next theme that we see is in gathering information. There are a lot of ways in which AI can be used to just crunch very big data sets. And here I want to particularly touch on big data sets of images from on-the-ground images, like camera traps that are used to monitor biodiversity, like here finding a deer. You can keep track of populations of species at scale using AI algorithms and understand biodiversity to a much more, in a much greater degree, thanks to tools that enable you to scale up data collection and really gather data to inform ecological decisions. Same thing with estimating carbon stock or other aspects of land use, which we'll get into a bit more later, gathering that imagery from satellites and then processing it at scale using AI. So taking unstructured information, making it usable with AI. Forecasting, time series predictions. For example, the UK's national grid has used AI to predict both the supply of electricity, which is variable if you're using any solar and wind power, which basically every electrical grid is now. So predicting the supply of electricity and also predicting the demand. So the UK cut the error rate in predicting the demand for electricity in half approximately using new AI algorithms. So we're just seeing all of these sectors really integrating AI to solve particular long-standing problems. Speeding up simulations. We have very good models for the Earth's climate and weather and various other physics-driven simulations that are important across the world. For example, in electrical grid planning. And these simulations are accurate because we understand the physics, but they can sometimes be very slow. And again, we'll get into this more later, but there are ways in which AI is being used to speed up these simulations and make them run more effectively at scale. And then perhaps the most sort of blue sky innovation is using AI to help innovate within the space of clean tech and climate technology. For example, suggesting materials to use in batteries, perovskites used in solar cells, and various other applications. Like my lab's works on catalysts, among other things here. And here, the goal of AI is not to replace chemical experimentation. It's to speed up the process of deciding which might be good materials to try. So these are all different ways in which AI is being used to help advance climate action. I want to talk about the other side now in this two sides paradigm, the way it's often presented. These are various projections of energy consumption associated with AI. And there are a lot of different estimates, but you can see that they're all really taking off. And to put some of these numbers in perspective, they are starting to get into the same order of magnitude as total global electricity consumption. Like, not all of total global electricity consumption, but like a reasonable fraction. And certainly a reasonable fraction if you look at any particular country, like the US or low-income countries, especially. So these curves, which are getting really high, are definitely a major factor for both people producing electricity and also people thinking about the emissions associated with electrical grids. And let's look into a little bit more detail as to what is involved there. Well, here we looked at all the different ways in which AI is connected to climate action in positive and negative ways. And I'll get more into some of those other components a bit later. But what I want to draw attention to here is that in creating and using an AI algorithm, there are several different phases, which is worth bearing in mind. There is the phase of development, where you are sort of iterating on what AI algorithm am I going to use. And that is done very rarely, because once you've decided on something, you can keep on using it. But it requires a lot of iteration, and it uses a really large amount of energy compared to the other phases, which is training. So fitting a model to data. AI algorithms are generally speaking now meaning some form of machine learning algorithms. They're generally being fit to data, which involves a relatively large amount of energy by comparison to, again, the thing that's done most frequently, which is inference, which is actually using the AI algorithm. And what I want to contrast here is this is done very frequently, and it uses much less energy than this, which is done less frequently, but uses more energy than this, which is done less frequently again, and uses more energy again. So all of these play a role because sort of the two sides go in different directions. So it's not just a question of like how many times does one use an AI algorithm, it's also these other things. Anyway, and I'm getting to get into like what those algorithms are in a moment, because that's sort of one of the key points I want to focus on. But before we get to that, I want to talk about the other ways in which AI computation affects sustainability, broadly speaking. And in the climate change context, there are embodied emissions, so emissions associated with manufacturing and physical activities, associated with mining and production of materials for use in servers, transportation of those materials, and disposal and recycling as well. So those are fairly significant. There's also water usage, which is another sustainability implication. And it depends upon how something is set up. For example, water usage can be much more salient in very dry areas, which are often actually like hot, dry areas can be good from a perspective of like a lot of solar energy sometimes, but then you end up with very little water for cooling the data center, and so you end up with sustainability trade-offs there. Very, very interesting topic. But these are both big factors. Okay. So why, I just talked about each of these components, and they are both in some sense true. Why do I think this framing is wrong? Okay, so there is a lot of stuff that comes under the heading of AI. And let's think about AI like a menagerie of different animals. So if you're looking at your menagerie of different animals, there are elephants, and there are very different animals, like bees, for example. AI, as it's defined formally by the OECD, is any computer algorithm that makes decisions, recommendations, or predictions on the basis of a defined set of objectives. That's a very broad definition. And in practice, also, it's a very broad definition. When people say AI, they mean lots of different things. And oftentimes, when people are talking about something like this, the reason why this framing works is because in the first part of the sentence, they mean one thing by AI, and in the second part of the sentence, they mean another thing. And so on one side, you have AI algorithms that are like elephants. And what I'm gonna draw the analogy to here is the algorithms that are often in the news or on social media a lot now. Like ChatGPT or other large language models, DeepSeek now, Midjourney, other image generation algorithms, etc. In some sense, those are the elephant in the room. They're often being talked about. And on the other side, there are a lot of other apps, like UNets, which are used for picking apart images into different segments. ResNets, which often are used for image classification. LSTMs, which are used to make time series predictions. Physics-informed neural networks, which are used to engage in contexts where there's some physics or engineering involved. Interpretable machine learning, which is a broad theme which encompasses a lot of different applications of machine learning and AI in contexts where we need to understand how a decision is being made. The key point here is that just like there is a diversity of animals and that an elephant is very, very different from a bee, so there is a huge difference between these kinds of AI algorithms. From the perspective of simply size, which means number of parameters, like the number of numbers involved in defining the algorithm, and then also the number of computations going on, which is associated to the energy usage. The difference between different kinds of AI is only the same thing as an elephant to a bee, or actually even bigger than that. These algorithms can be literally billions of times bigger, like more energy, than these algorithms. There's also fundamentally a difference between what these algorithms are trying to do. And it's just as like an elephant isn't just a bigger bee. These algorithms are designed to do something very different from these algorithms, generally speaking. These algorithms are designed to do generation of things. This is increasingly what people think of in sort of common parlance when they say AI. Generation of text, generation of images, generation of video. That is very different, actually, from what these algorithms are being used. That's often classification, like does this image have, does it show water? Does it show a cat? Optimization. Are we going to, how do we optimize the process of steel and cement manufacture? Prediction. What is the demand for electrical power going to be in the next hour, etc. And here's the kicker. Well, I get the kicker in a moment, but like the scope is also different. I guess I want to emphasize the goals are often extremely broad and general purpose for these kinds of algorithms, and they sort of claim to be able to do all the different things. Whereas these algorithms are generally designed to be somewhat narrower scope. They are designed to solve a particular problem and do not focus on overarching goals like take in the entire internet of data and purport to answer any question that a user might have. So if you think about how these are actually being used, these algorithms, these elephants, are not being used very much in climate action, but actually all across a lot of societally relevant applications. If you think about what factories are using, how AI is making a difference on the ground in most sectors, and has been for years, it's not the elephants, it's the bees. It is algorithms that are designed to do very specific things, have very narrow scope, and aren't about generation at all. They're not about generation of text, images, or video. They're about classification, optimization, prediction, something like that. And if you've ever actually asked ChatGPT to do something like, optimize your factory, it's not the right tool for that job. These elephants are not the same as bees. if you are a farmer looking to optimize your agricultural yield, you are going to need specialized algorithms and very specific ones. You're not going to need an elephant. You're going to need a bee, just like you would want a bee to pollinate your crops, and you wouldn't want an elephant to do that. I feel very strongly that oftentimes the debate about AI and climate change is confusing different kinds of AI. And we need to recognize that the high computation AI is sometimes useful, but it's only sometimes useful. And when we talk about advantages and disadvantages of the AI, oftentimes there's a lot of stuff being conflated here. And in particular, I see a lot of the dialogue around growth of AI recently sort of assuming that the AI use cases for society look a certain way. And this is the correct approach. To have a lot of different ways that AI is being used in many different sectors, many different use cases, and have it sometimes be big generative AI algorithms, but mostly small specialized algorithms to tackle lots of specific tasks. But what I see often being assumed is that what we actually are doing is what we need is enormous AI algorithms to do everything. And just like those farmers, you don't actually get a win, either metaphorically or in practice, through replacing bees with elephants. LLMs and other generative AI algorithms are just not the right tool for most jobs. They're the right tool for some. And oftentimes, the policies like let's build more data centers to advance AI, like really large-scale data centers, or every country needs their own version of ChatGPT, are sort of missing the point for what people are using in a climate perspective, but also just overall across most sectors of the economy. So this is the wrong approach. Let's use LLMs for everything. There's a modified version of this, which is also the wrong approach, which is AI uses a lot of energy, by which I mean here large-scale generative AI like ChatGPT uses a lot of energy. So let's actually make smaller versions of ChatGPT. Here we have smaller elephants. Just like you don't end up with a bee if you make a smaller elephant, you don't end up with a specialized AI algorithm that's designed for a non-generative purpose if you make a smaller generative AI. Smaller LLMs are still not the right tool for the job in many cases. Similarly, people have also talked about adding things on top of Gen AI algorithms to somehow make them a little bit more like bees. This is also not a good approach in general. Fundamentally, we need this situation where there's a mixture of different AI algorithms, but probably most of the time, we're not going to end up with elephants. And when people are talking about AI being integrated into everything, and they mean something like this, a lot of those elephants, I worry, are going to end up being white elephants that take a lot of resources, but aren't actually giving back to society. Let's look at some examples here of what I mean when I say that mostly we don't need the elephants. So this is an example from our partnerships with organizations across the world like NASA Harvest and the European Space Agency's World Cereal Project. These organizations provide information to governments that are looking to shape agricultural policy. And a key aspect of governmental agricultural policy from the US to West Africa, which is where these pictures are from, is to understand where crops are and what they're producing. And especially important as changing weather and climate patterns threaten food security across the world. This kind of data is provided for the whole world thanks to organizations that do satellite monitoring, like NASA Harvest, like the European Space Agency's World Cereals Program. This has been invaluable for the US maintaining food security, for example. And what you need when you have the satellite imagery is to actually be able to analyze it at scale. So here's a crop map, for example, for the government of Togo. And this was created through AI algorithms. But in order to have AI algorithms work in these kinds of contexts, you need tools that can work with large amounts of satellite imagery and label that into relevant information, like what is this crop? And here I want to talk about what the tools are that are actually being used. So, and I want to give a sense of scale, because I remember we were talking about elephants and bees, and like what is the size of one algorithm? What was the kind of algorithm being used? So ChatGPT, DeepSeek, other large language models, you should assume they have about 1 trillion trainable parameters. There's a little bit more for ChatGPT and a little bit less for DeepSeek, though it's actually a little bit complicated there in that DeepSeek ends up using more energy when you ask it a question than ChatGPT, but it used less energy to train, and it's complicated. About 1 trillion trainable parameters. A large general purpose, a sort of standard general purpose computer vision algorithm that is designed to process, like classify images for a general task has vastly fewer parameters. 100 million parameters be standard. That's a vision transform. What are people actually using? Well, for this task, they're using an algorithm that we developed, which is called Presto, and it has about 1,000 trainable parameters. And the reason why they're using it is not because it uses less energy, though that's an advantage. It also makes it more scalable across the world. They're using it because it's actually better than the other approaches. These other approaches don't work. Presto works. So when I say that people need bees, specialized algorithms that are designed to do something focused and actually are much smaller, here we have an example where the algorithm that's being used is literally 1 billion times smaller than ChatGPT and does a better job, vastly better. ChatGPT wouldn't work here at all. And this is the case for mapping crops. It's actually the case for other kinds of satellite imagery related tasks, like assessing fuel moisture in wildfire, preventing wildfires, tracking trees across the forestry industry, measuring algal blooms, which are a major impact associated with climate change as well. And for all of these tasks, using the small focused algorithm is the right approach from simply the perspective of accuracy. Then you also end up with greater scalability, because these governmental agencies that are trying to use these algorithms, they don't have the resources to actually use something like 1 trillion parameter model. They would have to apply it across the whole world. Even OpenAI doesn't have the ability to do that at scale. So anyone who's trying to do something scalable needs something smaller, but also it's actually more accurate. And the reason why it's more accurate, it's not magic. It's through the design of something really focused on the task at hand. I'm going to get into this a little bit more later, but really focused on what the problem is and focused on the specific challenges of that. So this is using the structure of remote sensing data, which has many different sensors at different points in time. And the way in which this works is actually leveraging the fact that a satellite is taking a picture at several different points in time, and it's using many different kinds of camera and kinds of sensors to get information on the ground. So that could be synthetic aperture radar alongside RGB channels, sort of normal RGB image. It could be elevation map, precipitation maps, other kinds of information, all layered on top of each other. And then seeing that over time and using that structure is actually key to making an algorithm that works. By contrast, a general purpose image processing algorithm is not focused on these challenges associated with particular data of satellite imagery. And so it's not able to take advantage of that information. So you see here, where we're really focusing in on the problem is key. And the way in which this works actually is the strategy called masked autoencoding, where we cut out pieces of the data, like particular time steps or particular features coming in from different parts of the satellite. And we try to reconstruct those from the ones that we're seeing. And by doing so in a really massively scaled way, the AI algorithm learns to pick out useful patterns in satellite imagery specifically, that then make it possible for it to do a lot of downstream things. This is a form of pre-training, and the pre-training means that you get, in the interior of the AI algorithm, you get a representation of the data, so a compressed representation of the data, that then can be used for lots of different downstream applications. The downstream applications could be in monitoring agriculture, fires, trees, etc. And again, the way it works is because we've designed it to meet the needs of the data. Let's look at another example. We've also, in my group, worked extensively on power grid optimization. So power grid operators need to know how much power to produce at every generator in an electrical grid. This is the set of equations that they need to solve in order to do that. It is what's called a non-convex optimization problem. And for any computer scientists in the room, you may know that that means that it is hard. Non-convex optimization problems are not solvable, generally speaking, in any fast way. And since the exact solutions take too long, electrical grid operators typically will simplify the problem. They will actually linearize it, which makes it simpler to solve, but it also means that you get a bad solution and you end up wasting power, especially with solar and wind power. Wasting power in the sense of producing too much. It costs more, it's a waste of electricity, it produces more greenhouse gas emissions. Bad across the board. Why can't we just use AI to solve this? Well, actually, normal standard AI approaches, like a deep learning algorithm that just tries to solve this, would normally fail completely. And why do they fail? Well, there's this little subtle point. Again, this is for the data scientists, computer scientists in the room. Normally, if you were trying to use an AI algorithm in a sort of naive way, you might be like, I'm trying to minimize this thing, which is like the cost associated with producing power. And I have to satisfy these constraints. These constraints are, by the way, that there is enough power to meet the demand and that the power flows normally with respect to the engineered electrical grid. And normally you would, in a standard deep learning implementation of this, you would say, I'm going to try to minimize this and try to minimize the violation of these constraints. And so you'll trade off in some sense between minimizing the cost and violating the constraints. And that is a terrible idea in this particular context. And the reason is because if you violate the constraints at all, you violate the system physics of the electrical grid and it breaks. You have a blackout and people die. So nobody would ever use a normal AI algorithm to solve this. And certainly you would never use ChatGPT, which would not give any kind of sensible answer. It would just make up some numbers. The way that we have designed to work with such equations, however, uses something called implicit differentiation to actually integrate these constraints into the solver, into the AI, by really integrally using the structure of the data, in this case, the engineered system of the power grid. And this makes it possible to solve these optimization problems 10 to 100 times faster than traditional methods without violating the constraints. So if you are a power grid operator, you can actually use an AI algorithm and you don't have to run the risk that your grid is going to break and you're going to have a blackout. And we can more broadly solve optimization problems that look like this, subject to hard constraints. So it actually leads to an interesting and broadly useful AI algorithm just by thinking about what is really needed in this particular problem. I'll give one more example. And this is, as I touched on before, the climate models are often very slow, even if they're accurate. This is data from our partners at Environment and Climate Change Canada, which is climate and weather modeling for the nation of Canada and for modeling the world overall as part of that. And you can see the grid here, the data, is like, you can see it's very pixelated. And the reason is that this grid is big. So if you were, for example, trying to understand the climate and weather trends in Columbus, you would have a prediction that is actually a significant amount of the Midwest. Like you would have all of Ohio instead of your particular city. And that's a problem because oftentimes, if you're trying to understand climate and weather trends, they're actually very different at local resolution. So you need something that's much more fine-grained. It's very hard to get these kinds of predictions. So we've integrated AI into the especially slow part of Environment and Climate Change Canada's models, which is radiative transfer, and it has to do with the amount of energy going into different parts of the atmosphere and the ground. And this is an especially slow part of climate and weather models. And this makes it possible to speed them up. And this is incorporating some known physics about how this works. And we're integrating that into the models that are being used in order to create faster algorithms. And here I want to note that not only is AI not sort of creating more computation here, it's actually saving computation because these things normally take months to run, even on supercomputers, and we're making them run much faster. But that's by virtue of using the right AI tool for the job, which is a small algorithm designed for the specific task. There's another way that you can do this too, which I quickly want to mention. It's like when somebody in a movie says like enhance that image, and you can do that too with AI. But you have to design special algorithms for that too. It's called super resolution in the field of AI, and it's called statistical downscaling in the field of earth science. And that is to improve predictions that look like this to make them look sharper like this. But the standard AI approaches to do this actually don't work with climate and weather data because clouds look very different from like people's faces. And so we had to design special methods that do this, that respect the physics, like conservation of energy, conservation of mass, and so on, and also can deal with sort of arbitrarily high resolution images without a lot of data for that or any data. And this leverages something called the Fourier neural operator, which is to do with differential equation solving. But I want to touch on the overall themes which we see here for how you make a difference using AI in a real-world application, like in climate change, but this holds in so many other really like key sectors of our economy. AI needs to be designed in many cases for problem-specific goals. If you try to solve all the problems, you often end up solving none of them especially well. And also, in many of these cases, we just don't need generative AI. In some cases, we do, to be clear. I'm not trying to say that one never wants a chatbot or a cool image generator. One absolutely does sometimes. But in so many situations, what we need is a specialized algorithm to solve a real-world task. And that real-world task is something like optimization or prediction or classification. It's not generating something. And it's designed based upon application-specific evaluation metrics too, designed for to meet the needs of a particular user community. It's very narrow. And it builds in as much knowledge about the problem and about the user needs as possible. So this is a paradigm that I'd like to see more and more in AI innovation, designing for problem-specific goals. I think oftentimes AI as a field has gone broader. Let's try to solve the general purpose problem. Let's try to take the entire internet's worth of data and use that in something that's big and tries to do all the things. But actually, the most impactful algorithms often end up being those which try to do one thing really well. And that's what is being used in practice. So turning back to the problem as it's often framed, AI can help solve climate change, but use a lot of energy. These are two different kinds of AI. Oftentimes, the AI that is helping solve climate change is not the AI that's using a lot of energy. And that's not because, again, we are trying to have it be more energy efficient. It's just because that's the best AI for the job. But there's another reason why I think that this statement is misleading. And that's because AI is affecting climate change negatively, not just through energy use associated with AI. AI is also used extensively in fossil fuel exploration and extraction, sometimes giving a 5% production boost. There are other ways in which AI is sort of systemically changing society in ways that aren't aligned with climate action. AI is ubiquitous in enabling online advertising. The fast fashion industry in particular is really reliant upon AI online ads. Like all of online ads are driven by AI, but fast fashion is a major contributor to climate change. Fashion is the third biggest contributor to climate change after agriculture and construction as an industry. Really, online advertising is essential to fast fashion specifically. So we're seeing massive profits for certain actors associated with this kind of industry. So there's fossil fuel extraction and exploration as well, as an estimated $500 billion in additional profit for the fossil fuel industry, thanks to AI and advanced analytics already. And there are more complicated ways in which AI is changing behavior associated with climate impacts. Self-driving cars are often seen as a sort of flagship application of AI, and they are probably going to make climate change worse. Now, there are reasons why self-driving cars can be useful, like maybe from the perspective of public safety sometimes, but it is likely that they're going to induce more driving because they will make it easier to drive, and it's expected that people will just drive more, even if each mile driven becomes a little bit more efficient. However, the same algorithms, the same technology can be used in self-driving buses, for example, or maybe self-driving trucks. That's a bit more complicated as an impact. But thoughtfully thinking about how we can integrate this technology into transportation sectors is really key to the climate impacts. We shouldn't think in terms of sort of the impacts being inevitable. Oftentimes, there are multiple ways that you can use a technology in a profit-aligned way, right? Like self-driving buses, great business proposition, just like self-driving personal vehicles. But thinking about how we're deploying the technology is really key. And so I think what I want to leave you with here is that AI for good doesn't just mean adding some new good applications of AI. This term AI for good is often thought of as like, well, we're going to do AI for business as usual, and then we're going to do AI for good. And that's not a very good idea if we're thinking in terms of shaping how new technologies are impacting society. And to be clear, I'm not saying that we as a society should just like forbid the fossil fuel industry from using AI, but we can incentivize certain applications of AI and de-incentivize others. And also, as technologists, we can think about what applications we are enabling and which ones we are facilitating, bearing in mind that all applications of AI can be shaped with climate in mind. So I want to summarize these 3 key takeaways before leaving you with some additional resources. First of all, that high computation AI is actually only useful sometimes. It is sometimes very useful, but mostly when people talk about AI being used in their particular sector right now and having an impact, it's actually not that AI. And we should be thinking about a sort of diverse menagerie of AI algorithms where most of the time we're looking at small specialized algorithms because that's what is needed. And then thinking about AI being designed for problem-specific goals, thinking about the innovation landscape in computer science and in AI being one where we really need these sort of task-specific innovations, because that's what people are using. And then recognizing that all applications of AI can be shaped with the climate in mind. And it's not just about adding some sort of socially positive applications. And sort of recognizing that all of these decisions are being made implicitly, even when we're not making them explicitly. So some additional resources. As mentioned in the intro, I am a chair and co-founder of the nonprofit Climate Change AI, which catalyzes impactful work at the intersection of climate change and AI, and machine learning. We have a lot of resources if you're interested in learning more about the space. Resources aimed at researchers, practitioners, policymakers, different kinds of audiences. We have events, including our next event will be in Singapore at the International Conference on Learning Representations. It's one of the big AI conferences. And you can stream it for free online as well. You can look at 1,000 past papers from, that's from the research community, from the private sector, a lot of different entities publish papers in our events. And they're all peer reviewed and you can search through them online. We also have a summer school, which brings in people, not just students, at any level from any sector to learn more about this intersection of climate change and AI. People come from different kinds of sectors, one side, the other side. We have funding programs. We've given away now about 5 million in impactful catalytic research and research deployment pipeline. And if you're interested in staying informed about news in this intersection of AI and climate change, you can check out our newsletter, which is monthly updates on what's happening in AI and climate change. We also have a blog and a community platform where you can stay in touch with people from all kinds of different areas around the world and all kinds of different sectors and share expertise and questions and knowledge. Many startups form, for example, through our community. You can learn more of all these things, including we also now, of course, are on Blue Sky. I forgot to update that. Yeah, so I would encourage you to check out resources at Climate Change AI. Finally, since I know there are a bunch of policymakers in the room, I wanted to highlight in particular a report that Climate Change AI worked on for the Global Partnership in AI, which has been endorsed by all of the member governments associated with the Global Partnership in AI, which is an OECD initiative. And here we were trying to provide recommendations for governments on how to facilitate AI, the AI and climate change ecosystem. And there are a lot of different things that we considered here. I want to give a few recommendations, highlight recommendations. But again, this is like a 100-page report. You can check out the full set of 50 recommendations there. But some selected recommendations are, there's a real need for improving data standards and data sharing. Task forces associated with particular sectors, platforms for data sharing. Oftentimes, there is a need for centralized players to provide interoperationality and the coordination between different entities that would benefit from a centralized structures for data. Like if you have a lot of different companies that all have data and could put that into a pool for use by the public, that would benefit sometimes all companies because you could use all of that data to develop AI tools, proprietary AI tools for those different companies. So data sharing is sometimes in everybody's interest, but there needs to be coordination on this. Standards for sharing, standards of quality, and coordination. Impact-driven funding. Oftentimes AI funding, there's massive amounts of it, is actually driven at this sort of blue sky general purpose AI innovation. Can't tell you how many tens of billions, hundreds of billions, probably trillions at this point, are being devoted to data center creation, but not to collaborations between AI and like the transportation sector. And it would be really valuable to have more impact-driven funding for AI research and innovation. Similarly, cross-sectoral innovation centers bring together public and private stakeholders to incubate projects, facilitate collaboration, and obviously start new enterprises. Building AI capacity and literacy is also key because many industries want to adopt AI, but they're not sure how to do that. So often implementing AI in the wrong way. This is one of the reasons why we're using elephants for everything. It's because everyone thinks they need AI now, but they don't know what that means. And so what they see is ChatGPT. And so that doesn't mean that everybody needs ChatGPT. We need more upskilling and secondment programs to integrate AI expertise into relevant sectors and industries so that people can decide. Sometimes they want a chatbot, but sometimes they want an optimization algorithm. Establishing best practices for responsible and participatory design, ensuring that it really is user-centric and think about what the users are, like end communities that are being affected. And then considering positive and negative climate impact as one factor in shaping new technology development. Shaping the risks associated with that, considering the risks associated with that is one factor associated with new technology incentivization. Thank you very much for listening. And we have about 10 minutes, maybe 15 minutes for questions.
Yes, we do, David, and thank you very much. That was really good. I really appreciate the way you've done a deeper dive into AI and what that means. I mean, in our previous webinars in the series, we've been talking about AI like it's a monolith, essentially. And it's really helpful to think about the elephants and bees that comprise AI. And I appreciate the resources and policy recommendations you made at the end, because that really anticipated one of my questions, and maybe I'll let you drill down a little bit, is that how does a typical user of an AI or somebody who wants to use AI, a person or organization, help distinguish between whether they need a bee or an elephant? And maybe you can do a little bit more deeper dive into some of your recommendations and like make it very practical for people. Like, how would you go about doing this?
Yeah, so I mean, I think first of all, you need to think in terms always of what it is that you are actually looking for. And here, I think that people oftentimes confuse information presentation with information generation. So, for example, I was asked by the government of Canada to comment upon a new initiative that they were thinking about called Biodiversity GPT that would enable the government to make decisions on what was going to happen to Canada's biodiversity according to particular kinds of decisions, right? You know, you're making decisions on land use associated with forests and agriculture and blah, blah, blah. And what they actually needed was to answer various really tough questions about how certain decisions were going to impact biodiversity. What they thought they needed was a chatbot that would answer those questions. But actually, the answers to the questions had never been created. There was no data source that the chatbot could draw on, even if it was a perfect chatbot. And the questions were sufficiently hard that they require expert ecologists and experts on land use to be the ones creating the answers. And they require significant work by those experts. They're not answers which even exist yet. So there isn't actually a way for AI to answer some of those questions at all. But there are two ways that AI can be relevant to them. First is, the primary way is creating a lot of data that can help those experts make their decisions. gathering data on where is biodiversity now, what is land use now, and like really creating tools for mapping out lots of stuff, like I was talking about with Presto, for example. And then what they actually wanted is a really easy chatbot that would help interface with some of that information once it had been created by experts. But that's not the function of the chatbot. Mostly what they wanted an interface, but they thought that the interface was going to answer the questions for them. And I think a lot of times what people think they need is an AI algorithm that just answers all their questions. But actually, in order to be effective, that kind of thing is normally just a software wrapper, sometimes a chatbot, sometimes just a good website, which surfaces insights that were created with much more work. And that's either done by experts, human experts, and sometimes the human experts need AI-gathered data, like data on where is the biodiversity, or it's done by AI algorithms, it's done by specialized AI algorithms, right? Like if you're a factory operator, you don't need an AI algorithm that will answer any question about how you should operate your factory. You need an algorithm that will be able to work out the best way to operate this machine according to these constraints. And you can give it this data and it will work out the answer. But the way you interface with that algorithm, you want a software engineer to make something user-friendly for you. And so you need to think about what the actual problem is. The hard problem, is not the user-friendly part. It's the optimization algorithm. So in every case, think about what data you're giving the AI algorithm and what data you really want out. And in some cases, it will be an optimization algorithm. In some cases, it will be a classification algorithm. What is there in this image? What is there in this data? Is the market going to go up? Is the market going to go down? So maybe time series predictions could be integrated there. But it is different often from how it is presented. And I think that there's often that confusion going on right now.
So this raises a question for me as an educator. So I'm trying to train my students in my domain area, which is sustainable transportation. I'm teaching them transportation theory, I'm teaching them methods, I'm teaching them geospatial data analytics. How do I incorporate, AI into this? I mean, what is the portfolio of skills that people in a particular domain science will need to know in the future in order to use AI in an intelligent, thoughtful way?
It depends on the particular sector, right? Like if you're working with transportation, like for example, transportation sectors long used algorithms that could be thought of as AI, like traditional optimization algorithms. Nowadays, there are deep learning-based optimization algorithms which are being used as well. There's like predictive maintenance of railroad tracks, but there's also like deep learning-based optimization for route planning to optimize train schedules, bus, truck schedules, etc. And so I think there's a lot of optimization in that particular sector. But if you're thinking about other sectors, maybe it's something else. Maybe if you are in the agriculture sector, you want a lot of computer vision-based approaches. Like you want computer vision for monitoring satellite imagery. I didn't talk about robots, like controlling robots on the ground. So maybe the control algorithms, but also like robotic sensory systems. Those are different areas of AI completely. And it really depends upon what your students need to be engaging with. What I can say is that teaching them how to prompt ChatGPT is not going to deal with any of these things. That may enable them to create a user-friendly report with some information that was already created in another way, but it's not going to answer these fundamental questions because they're just not the tool. Those tools aren't capable of doing that. Yeah.
Oh, but a lot of what my students need to solve are what we call wicked problems in social science, where we have, value stances that are embedded and
Yeah.
difficult trade-offs to make. So there's nothing to optimize. There's no single thing to optimize. So what's your suggestion there in trying to tackle some of these wicked societal problems?
Wicked societal problems have to be dealt with by people. They're fundamentally like oftentimes people try to use AI because it sort of eliminates the need for thinking about values and goals. It's like objective, and that's wrong. It's just using them just in a very non-transparent way. You don't know what the values are and the goals are in an AI system. It's probably the goals of like 1 million people on Reddit that went into like if it's a general purpose AI system. Right? It's definitely not objective. And so the answers that you get out of those kinds of systems are essentially just random drawing upon some sort of data somewhere. If you try to optimize a really controlled system, like a policy-making system, you can sometimes do it, but it needs to be really tightly simulated. You need to have really like a very clear idea of what is going on. In societal systems, they're too complex. You can optimize a factory because you can have a digital twin of the factory. You can have a complete simulation of the factory. Trying to optimize a country, you can't do that. But you can gather data on different pieces. You can like analyze mobile phone data subject to privacy constraints. And then you can use that as an input to your expert-driven model. So there are tons of ways that AI can pull information for you to make better decisions. But the human should be the one making the decisions, not again, just because you don't want to have AI algorithms controlling things, but because the algorithms just don't make good decisions if they don't have the ability to do so.
Right. Okay, I'm gonna turn over to Jordan now. We have a couple questions from the audience. Jordan,
I can
are you
read the
there?
questions if you want me to just go through them.
Jordan likes to do it. Go ahead,
Yeah,
Jordan.
go for it. Go for it. I've been talking a lot.
Yeah, I'm happy to prompt you. So one of the questions we have is the AI tools many of us use in education, such as ChatGPT, Perplexity, and Notebook LM, are considered high computation models. Do you think using these models for everyday educational tasks is ethical? And how would you respond to someone who argues that the use of this kind of AI is unethical due to its energy consumption and climate impact?
I mean, a few different things. First of all, it really depends on how much you're using something, what the climate impact actually is. It's not like you use ChatGPT once, you suddenly have destroyed 1 million trees, right? There are different estimates about how much energy is actually used by these tools. And for reference, we don't actually have any knowledge about how much energy ChatGPT uses because OpenAI refuses to be open about any of these things. You might want to pick a tool. There are many tools to choose from. You might want to pick a tool where they're actually public about the energy usage. But I mean, I'm primarily worried about ethical implications of AI in education from other perspectives. I'm worried about it from the perspective of IP violation, that these algorithms were typically created using media without consent. There are a lot of lawsuits going on about surrounding that. And that in some cases, they're not reliable at all. And students are often learning that LLMs are a form of search, and that's not true. They are not a search algorithm. They create something from scratch, which may or may not be true. Often, if you ask certain kinds of questions, they are more likely to be true than others. So I worry about those kinds of ethical implications more than I worry about energy usage for any particular application in education. But I think it really depends upon how much you're using it. And I would do some back of the envelope calculations and also compare it to other stuff, right? Like sometimes when people talk about digital technology and energy impacts, it's a little bit divorced from what the alternatives are, right? Like I've heard people say literally like, don't stream Netflix. It uses so much energy. Whereas the alternative for many people is just driving to a movie theater where getting in your car actually produces more emissions than streaming the show ever would have done. So I would think in terms of like actually doing a back of the envelope calculation, we sometimes have a very poor idea of what the order of magnitude is for these things. And we as individuals often have much less agency to have a large impact through these kinds of actions than we might think. So you should definitely do the calculation. It might be higher than you think, but it also might be lower.
Great, thank you. I have time for one more question. From the audience, can AI be used to present using an avatar in real time? What would be disclosed or policies around that?
So this is not necessarily within scope for this talk as much, but I can talk about the energy implications of that or the computational implications. I'm actually a bit more worried for such applications, which I would generally put under the term metaverse because that's how Facebook retitles such things. Like maybe we're all going to have avatars and we're going to engage with each other. There's some advantages to these ideas, like it reduces travel but air travel, potentially, not completely clear. And so that can actually have a positive climate impact. But I'm not clear that it actually is reducing air travel. It may just be a more energy intensive version of Zoom. I'm also not completely clear that people really want avatars. This has been tried for several years, and people keep on not actually using them that much. And whenever I've been in a situation where there's some avatar platform of engagement, it's also extremely inaccessible for people who have low computational bandwidth, which is, most of the US as well as most of the world. I don't want to download a gigabyte application or a 100 gigabyte application in order to be able to engage in the metaverse. And so I think we should be thinking oftentimes in these computational questions, not just about energy implications, but about who actually has the computation to be able to do these things. In that case, the computation is mostly in the, it might be in the size of the application. It might not necessarily be in the AI processing, but all of these sort of very compute intensive tools are often just like pretty inaccessible to a large number of users. So who are we really designing for?
Right. Social dimensions of AI. AI is the new flying. It's only accessible to a small percentage of the world.
Exactly. And flying, the idea is you design something for elites and then it trickles down to everybody else. Still, most people in the US have never been on a plane or have a passport. Like, there's a limit to how much you end up having a true democratization of tools. But also, some of these things take a really long time to trickle down, which limits your
80%,
user base too, right?
yeah, 80% of the world has never been on a flight, never flown. Anyways, we have to end on that issue. Thank you, David. That was a very illuminating talk, and I think it really opened my eyes a bit about the right AI tool for the right problem. And I think that's an important lesson going forward. And I appreciate the resources you shared with our audience as well. So thank you for your time today. This is the third in 4 webinars in our series is AI Sustainable, and I invite you to join our last webinar. That'll be Friday, April 18th at 12 p.m. Eastern Daylight Time. And that'll be with Professor Mark Partridge, who's the C. William Swank Chair of Rural Urban Policy in the College of Food, Agriculture, and Environmental Sciences here at The Ohio State University. And he will talk about data centers and community development. Do they compute? So check that out on Friday, April 18th at 12 p.m. Eastern Time. Thank you all for joining us today. And again, thank you, David, for your talk.
Thank you so much for having me.